This is the first part of the module on natural convection or free convection based on chapter 9 of your eBook. This module will cover mechanism for natural convection, two very important dimensionless numbers, the Grashof and Rayleigh numbers, and flow over three particular geometrical bodies, flat plate, cylinder and a sphere, and simultaneous force and free convection. Previously in forced convection, we have convection currents induced by an external force like a fan or a pump. In natural convection, we also have convection currents but without the fan or the pump. How does the convection currents get induced? It's because of the net effect of the buoyancy force due to the density gradients, thus inducing free convection currents. The most common case is where the density gradient is due to the temperature gradient and the body force is the gravitational force inducing the buoyancy force. Now here, classic example of cold soda can in a warmer surrounding. You have surrounding air being cool, the surrounding air next to the can being cool and thus becoming denser than air further away, and warmer air taking its place. So we have here convection current downwards around the cold soda can. Eventually your cold soda will be a warm soda. The other example is a hot body like an egg or a potato. Yes, so we have the cooler air next to the egg or potato being lighter and thus rising, being replaced by the cooler air further away. So we have convection currents upwards. Yeah. The free convection flow velocities are smaller than those in forced convection, and heat transfer cannot be controlled like that in forced convection. Yeah. In forced convection, you may be able to control the velocity of your fan or pump of the air, yeah, but not in natural convection. It is tempting to associate less significance to natural convection, but in many systems involving multi-mode heat transfer, natural convection provides the greatest resistance to heat transfer and therefore plays a significant role in system design to reduce costs. You have to consider it, especially in heat transfer from pipes and from transmission lines. Free convection strongly influences the operating temperatures of power generating and electronic devices. Free convection is also important in establishing temperature distributions within buildings. Yes, in building arrays, heat losses or heat loads for heating, ventilating, and air conditioning systems. The design must consider natural convection in order to be economical in the design and effective too. Free convection distributes the poisonous products of combustions during fires. Free convection drives oceanic and atmospheric motions. So, the body force is generally gravitational in free convection, but it can be centrifugal in a rotating fluid machinery or the Coriolis force in atmospheric and oceanic rotational motion. Here, we only focus on free convection in this module, where the density gradient is due to the temperature gradient and the body force acting on it is the gravitational force. Note that the presence of a fluid density gradient, the difference density due to gravitational field, does not ensure the existence of free convection. Let's have a look at these two cases, special cases. We have a tank, closed tank of fluid, where the floor is at a higher temperature. The first case, the floor is at a higher temperature than the top. Yes. The density, of course, increases in the direction away from the gravitational force. Yeah. If the temperature difference exceeds a critical value, conditions are unstable and the buoyancy forces are able to overcome the retarding viscous forces. Now, heat transfer from the bottom surface to the top surface occurs. Yeah. Special, beautiful example is the Rayleigh-Bénard convection, which you can check out somewhere. The second case is different. We have a stable temperature gradient. Now, in this case, we have the top that is at a higher temperature than the floor. Yes, so the fluid near the top will be lighter and stays there, while the fluid next to the floor is denser. So we have a stable condition here, but eventually the fluid will reach an equilibrium temperature. How? Look at that and see what mechanism of heat transfer induce the equilibrium condition in temperature. Now, free convection flows may be classified according to whether the flow is bounded by a surface. In an absence of an adjoint surface, free boundary flows may occur in the form of a plume or a buoyant jet. What is a plume? A plume is associated with fluid rising from a submerged heated object, for instance, like heated wire, immersed in an extensive means infinite medium. Quiescent fluid, quiescent means velocity far away from the body is zero. A plume has zero initial velocity. A buoyant jet has a finite initial velocity. This heated fluid being discharged, as a horizontal jet, so it has the initial velocity, being injected into a quiescent medium at a lower temperature. Now, the vertical motion in a jet is due to the buoyancy force. Difference in density due to gravitational force. Example would be a warm water from the condenser of a central power station being discharged into the cooler river or lake. Now, schematically, the plume and the jet are shown here, where we have a heated discharge. Note here that x direction is vertical now. In natural convection, x is vertical and y is horizontal. In this module, natural convection coverage will focus on free convection flows bounded by a surface, with the classic example of boundary layer development on a heated plate immersed in an extensive quiescent fluid. Extensive means large amount of fluid, and quiescent means velocity far away from the body is zero. So, classic example here, let's have a look at the vertical plate. We have a heated plate which is at a higher temperature than the surrounding fluid. So the fluid next to the vertical plate is being heated up and becomes less dense, thus rises, and the cooler fluid taking their place. So we have convection current being induced here, the cooler surrounding fluid taking place with the lighter, warmer fluid which is rising. See? Unlike forced convection, the velocity is zero for y. Remember, y is horizontal, so distance far away from the solid body, the velocity is zero as well as there, because that's where the sort of like a leading edge. Okay. Now, when the fluid temperature is higher than the vertical plate, the opposite happens. The convection current is now downwards. Can you explain how this happened? Okay. So the governing equations are the same as those in forced convection: conservation mass, momentum, and energy, where inertia and viscous forces, energy transfer by advection and diffusion remain important. However, in natural convection, it is the buoyancy forces that sustain the flow. In forced convection, it's the external force like the palm of fan that is sustaining the flow of the fluid next to the solid body. So you can check out your ebook with the series of equations developing in the boundary layer equations. Note here in the boundary layer, the density is a variable, right? The buoyancy force is described by this term G, delta rho divided by rho being the density of the fluid. And we have the volumetric thermal expansion, 93 beta. It's a measure of the amount by which the density changes in response to change in temperature at constant pressure. So subsequently, we give the Boussinesq approximation to the boundary layer equation. Yes. So for ideal gases, the volumetric thermal expansion may be obtained with 9.4. It's just 1 over T. Note that T is in Kelvin. For liquids and real gases, the values for beta, the volumetric thermal expansion, may be obtained from property tables in the appendices. Yes. If Reynolds number provides a measure of the initial to viscous forces acting on the fluid element, here we have in natural convection Grashof number, which is a measure of the ratio of the buoyancy forces to the viscous forces acting on the fluid. Now, the Grashof number, or later we'll introduce to another number, the Rayleigh number, provides the main criteria in determining if the flow is laminar or turbulent. So consequently, knowing the laminar and turbulent will direct you to which Nusselt number equation to use and get your convective heat transfer coefficient for your 3 heat transfer analysis. In the next part of this module, we'll look at the natural convection in the cases for 3 geometrical bodies: flat plate. The flat plate can be vertical, horizontal, or inclined at an angle, flow over a cylinder, and a sphere.